Okay, welcome back, and good evening from the, the woods of Maine. Um, this is part two of the geology of Maine, uh, basically focusing eventually on the marginal way. It's going to be a while before we actually get there, but we will, sure enough. In any case, uh, I just got to say something crazy happened last night. We had this torrential thunderstorm. Just been like July has been the month of thunderstorms. In any case, so I booked it up to Shaw's parking lot because I was afraid if it hailed, I didn't want the car to get all banged up, and so I figured there's some cover there. And anyway, so the rain comes and it just hammers, and there was a few times the winds shifted. They started going different directions, and then the rain just stopped in the middle of this torrential downpour, and it was like I'm starting to think tornado. And then as I was driving away, I heard this crazy slurping sound, like sucking sound, and there was like this whirlpool over a drain that was like a foot or two deep, about 10 feet wide. I mean, when I say wide, like the whole swirl, but the actual opening, the actual swirl going in the drain was probably 2 or 3 feet wide. I mean, it was crazy. I'd never seen anything like that in a parking lot. I tried to record it, but hit the wrong button. Anyway, story of my life. Um, so this is part two, and we left off at Lips, which was right at the end of the Wilson cycle, because in order, quick review, pretty much the continents come together and split, and the only way to really split up a continent when they've been slammed into each other is a gigantic mantle plume, and those come in the form of lips. Big, giant, juicy lips right here. Large igneous provinces. They are fascinating. They have played such a role in the evolution of life. Um, every time there's a really big one, there seems to be an associated extinction event. So they are 100% game changers. Again, not Mount St. Helens, not Yellowstone, not Etna, not Mauna Loa. It is something we have never seen in historic times. So all we do see is that when they happen, they can cover incredible areas. Like, they could bury uh, the state of California in 2 miles. You could bury the United States, and I think it's 200 meters of lava in one of these eruptions. I mean, the entire United States. Think about that. That is a huge area. Anyway, so lips are fascinating, and they are uh, all throughout the geologic record. Come in different types, different sizes, just different. They're just crazy. They're literally a giant. It's like a giant zit at the base of of your skin, like not the ones that you can easily pop, but the ones that really hurt. And they're deep, and they just swell, and they just get gnarly, and they just begin to get angrier and angrier, and they start to just bust through. And when they do, they take pieces of the continental mantle or lithosphere, asthenosphere, pieces of it with it, and bring it up. That's where you get some of your diamonds, is from lips. And then they infuse themselves into the crust, and they cause all sorts of reactions. And like I said, the lips are just absolute game changers. So the cross section of a lip here, we're kind of looking at it. This is plain view, and then this is cross section. So I kind of would have gone backwards with this, but whatever. So this is looking down on it as if you were looking from a satellite. They tend to happen in triple junctures for one reason or another. So when you get a big giant lip comes up, it doesn't just break apart, in one side or the other. There seems to be different junctions that eventually form, and the junctions actually kind of probably are focusing on the areas of weakness in these, around it, and then the dikes start going up through it and then melting it, making it weaker, and then the dikes finally just merge together, and then you got your triple junction. And if you're looking at the basement of a lip, you're way deep down here, just very, very, very far down. Almost 100, yeah, maybe 120, 130 kilometers down, just deep, deep. Punches up, comes into the lithosphere, begins to interact with that. It begins to push its way through there, and then at which time it will end up lodging itself into the crust at the basement, and then it will start to melt some of that, find its way up through. It can come through as a dike or a sill or just a huge pluton or whatever, or it can make it to the surface. It's just many, many different ways it can happen. But anyway, this is a large igneous province, and these are on the scales of, like, this is 500 kilometers here. So they can be, thousands of kilometers big. So they are just massive. This is just another internal structure of a lip. Again, coming up from the lithosphere, the asthenosphere to the lithosphere, gets lodged into the lower crust here, begins to just pull pieces in, spread it apart. Of course, everything starts moving apart as it starts to drive its way up through. This is the mantle plume. It sort of convects in here, begins to cool down, and you have your first layers of differentiated material, which is lighter. Sometimes as you get the heavier stuff will also settle out a little bit, but without a doubt, you start to get differentiate different layers. These layers begin to convect in the magma chamber itself. They make a zone of around where it actually was injected in. This can cause metamorphism, localized metamorphism. This is where you're getting a magma generation zone. This is when you have things all reacting, and you're creating things that are going to eventually either be plutons or plutonic, or they're going to be make it to the surface. So, and in this case, you have some that have made it. These are volcanoes. These are upper mantle. These are upper crust magma chambers. And then this is the pile of sediments that the volcanoes have made. These are lips in the last 300 million years. It really have to do it like this because the amount of lips that go back in time, granted, they become less numerous as you go further back, and that's probably not from the fact that there were less of them. It's probably just the fact that they've been destroyed. It would make sense to me that the Earth is hotter as we go further back, therefore there's probably more lips. Maybe they're just not as well preserved. So in any case, these are lips within the last 300 million years, and you can see that there are plenty. The flood basalts on the continent, these right here, 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 and here, probably here too. These all erupted within a very short period of time, and these are known as the Central Atlantic Magmatic Province. So when you bring North America and Africa, and South America and Africa together, you needed to break this apart, and these eruptions are what did it. These were massive. We see them in the Connecticut Rift Valley here in New England. You go down to Connecticut, southern Mass into Connecticut to the ocean. It is a huge area of Jurassic basalt that erupted. By far the youngest rocks in that area. They're unmetamorphosed, which means they were never really buried deep. And they represent where the continent tried to split apart there. And it eventually migrated further east, and of course, and then the coastline is further east. But it could have very well been there. Newark, New Jersey, the New York City, the Palisades Sill is a gigantic one. That's a world-known basaltic dike that was associated with some of these eruptions that forced apart the Atlantic Ocean. I mean, it forced apart the continents that allowed the Atlantic Ocean to form. This right here, this is the Deccan traps. These are, we think, associated with the extinction of the dinosaurs. So when India decided to go over the Reunion hotspot, which is into here, it ended up melting the basement of the crust of the continent and blasted up through in a very short period of time. And that's the thing. Lips generally occur in less than a couple million years. And for instance, you know, most volcanoes on Earth that have been around for a while are tens of millions of years old, and they don't produce, you know, a 1/1000th of the amount that these things produce. So that's the weird thing, is that these produce literally hundreds of thousands of times more lava, but in a much shorter period of time. This guy up here, this is the Siberian Traps. I think we believe that this is the largest known one. Definitely the largest in the last 300 million years. This one almost killed us all. This one wiped out life at the end of the Paleozoic, 98%, and it pretty much took almost everything out. Like, we were 3% away from becoming just a lifeless planet, and somehow we survived. The mammals and the reptiles really found their footing right after this particular event. This lip literally just destroyed the Earth, poisoned it, burnt it, crisped it, heated it. I mean, just everything. The fried oceans. I mean, it was bad, real bad. But it gave rise to the dinosaurs. Because of this, we have the dinosaurs, and then, ironically enough, right here, because of this, we have the mammals. So it seems like whoever's at the top of their game when these things occur is probably going to be gone. So anyway, good luck to us when the next one comes. This is the Central Atlantic lip, like I was just talking about, right here. Again, you see that this is just, you know, these are connected. These used to be together, and when this erupted, it was part of the fuel to or motivation to separate these continents. These are lips in the last 500 million years, and we do this because you know, like I said, there just wasn't enough. The map would be too cluttered. So as it turns out, again, we have these lips in these same areas. Well, why is that? Because before the Atlantic was there, when this is hard to do in reverse. If you were to bring Africa and North America and South America back together again, and then pull them apart, as you were going back in time, that new ocean that forms when you pull them back apart, or the older ocean rather, is called the Iapetus Ocean. And the Iapetus Ocean is an ocean that occupied roughly the same area that we see here, albeit it was a little bit more of an angle. But anyways, we call it the precursor of the Atlantic. And in order for that to have been split apart, because at one point that was closed, you needed to have that those eruptions. And again, in these same areas, you have what we call the CIMP. It's this Central Iapetus Magnetic Province. And again, these lips come in different zones. Black is continental mafic. It looks like blue is oceanic lips. I believe that the yellow here is either silicic, continental, or intermediate. I'm going to go maybe it's silicic. And then these are intermediate continentals. They come in all sorts of different mafic, felsic, you name it. They exist in all different types. Lips between 500 and 1 billion years ago. Again, there's the CIMP right there. Oh, you know, I gotta go back on that. I made a mistake on this. This is not, this is camp. I apologize. This is camp because it's less than 500 million. CIMP didn't come around until, it's older than that. I think it starts at around 700 million. So I apologize. I got that wrong. I made the mistake, and it clearly says it right here. So somebody was probably throwing something at the TV while I was blabbing. But this is the Central Atlantic Province, and again, this is about 200 million years old, which I discussed right here. Anyway, apologies. Sometimes I get it wrong too. Anyway, so the central Iapetus magmatic province is much older. They have it here at 620 million. Yeah, again, between 700 and around 6 to 700 million years old is when this really started coming into action. Yes, 620 million. And it didn't just happen all at once. It took quite a while, and it happened at different times in different places. But generally, over about a 100 million year period, the Iapetus Ocean busted up. Again, you have some other ones over here associated with continental breakups and what have you. A lot of these at this time are associated with the breakup of the supercontinent Rodinia, which we're going to be talking about later. 1 billion to 1.5 billion. Now we're really getting deep. We don't see any real silicic ones anymore, and if they aren't listed. They're not categorized here. We are starting to go back into a point where there are plenty of lips, but we're only seeing some of the biggest ones preserved. And again, these are associated with probably some sort of a breakup between two continental pieces, or simply the continents could have moved over a hot spot, and that does occur. It's not always just a continental breakup. It can be there's two zones of upwelling on the Earth. They're kind of bipolar, and one is Jason, one is called Uzo, and they kind of stay kind of stationary. It's weird. We really didn't really know about them in great detail probably for the last 30 years. But in any case, when the continents do decide to move over them, they have a tendency to really cause a lot of problems with the roots of the continents, and they will sometimes bust through and cause massive flips. Like this one here might have been that. I think the Siberian traps might have been the cause of that, but those can happen. And I'm thinking that Rodinia came together about 1250 to 9. So 200 million. What would have been busting up? Maybe Colombia. Yeah, I don't know. I think this might be more from continental pieces also going over mantle plumes. 1,500 to 2 billion. I'm not even going to speculate what they are associated with. They're definitely associated with, again, the previous stuff, but I just could not tell you which ones are which. Looks like we have a couple of silicics here. This is interesting. Well, they're about 400 million years apart. Really, I think if I just started looking at if you have ones from the same time on different continents, probably they're connected. So we could do that, and that's one of the ways we tell when things are connected. But again, big lips, all sorts of lips all over the place. And then we're going back to 2.5 billion. They become less numerous in a sense, and we only have them on the Cratonic on Cratonic pieces, because you're getting back to almost the end of the Archean. And we know that this is some of the oldest crusts in the world. We know that this is some of the oldest crusts in the world, and we know that this is some of the oldest crusts in the world. So, surprise, surprise, it's where we see these lips. All right, so I need to check something. Okay, sorry about that. Had to check my ribs. So, why am I going on about lips, and what do they have to do with the picture I just put up here? They have everything to do with this picture here, because each one of these lines probably at some point or another involved some sort of a lip. And the reason I say that is because each one of these colors represents a mountain building episode. And if you notice, the oldest stuff tends to be in the center. Well, that's not entirely true. These right here are the Craton, the Cratonic pieces from the Archean. And these pieces came together at one point, and then they separated at one point. And basically, this whole area that you see here is the what we consider the nucleus of North America, or Laurentia. This is the nucleus. This is the Craton. This is older than 300 million years, and what we kind of base this on is we look at things that are older than the basically the Paleozoic. So if this is small Proterozoic to Archean age rock, this over here, the Rockies are 700 million years old. In this area, the Appalachians are between 6 and 3. So we don't consider these. It really needs to be kind of more or less a billion or more. That you would classify that as more of the Craton of North America. The western side and the eastern side, the final two colors, the purple and the brown, are orogenies that are considered to be younger than the actual core of the continent. So, in any case, so what happened here is this was the original. These were three pieces that, for one reason or other, came together, then rifted apart, and then came back together again. And that is recorded right here in the Trans-Hudsonian Orogeny at 1.9 to 1.8 billion years ago. There are actually other ones up in here that brought these pieces together, and other pieces here that brought these pieces together. But in the gist of it is that these two pieces came together and separated, and came together again. And then along the southern part of this of North America, or Laurentia, we're going to call it, we had a mountain building episode here of island arcs, and then we had another episode of mountain building episode here of more island arcs, and then we had the continent tried to rift apart along the edge, but it didn't quite make it, and then we had the continent of Amazonia come in and slam on this side over here and create the Granite-Ryolite Orogeny, which is right in here. So basically a series of mountain building events, and then right in here about 1.2 to 1.1 we have what we call the mid-continental rift, where the continent once again started to try to break apart, kind of like what it did here, except here it succeeded. Anyways, this over here is a series of island arcs that have been getting wedged onto the western side of the Craton, and then of course the Appalachian Orogeny happened in the Paleozoic. So anyways, to get this, we need to build North America. So this is what I'm going to do, and I'm going to try to go through this fairly quick because it's a lot of information, but it's pretty interesting. So what a mess it is. Again, you have all these different orogenies and faults, and again, it's just a mess. But again, this all had to happen in order for this piece, for something this large to exist. But you look at it, this was the beginning. These colors here, these are the oldest pieces of crust. They had an orogeny right here. They had a rift happen right here. They had a series of orogenies right here. They had orogenies back here. They had an orogeny here. And then, of course, we had a continent-to-continent orogeny right here. And this has all gone on in the Proterozoic time. And that's just a general overview. It's even worse. All right, so North American tectonic events from 2.5 to 1.3A. So the best way to look at this is, and sometimes it can get confusing, but the A and the B and the C, this is A, this is B, and this is C. So greater than 2.5 billion years, as I said, you had the cratonic nucleus of Laurentia, which consisted of these pieces right here. You had the Slave Ray, Superior, and then the Wyoming. And at some point, they split, and you can tell just, the shape of it is they match. And then they came back together and created this massive mountain range. The Trans-Hudsonian Orogeny is probably the biggest that, up until that point, that was probably the biggest one that occurred, at least that we know of. And it involved, here are the two continental pieces, it involved subduction to the east, with a series of island arcs, and then these eventually came together and welded together, um, which is what you see right here on this graph right here. So this is when it happened. This is how it happened. B shows after it had been completed, and you can see that these two pieces of continents here with the oceanic crust being subducted beneath of that, and that is represented right here. And then we have a series of mountain building events that happened on the southwest side or southeast side, as this looks, and that is represented by the Yavapai, the Mazatzal, and then the Granite-Ryolite Province, and they are represented right here. So from here to here, we go across. We got the continental suture right here of the Craton. We got the Yavapai right here. We got the Mazatzal right here. We have the Granite-Ryolite Province right here, and then the Grenville, which has not really happened yet, but that's going to be coming. But you can see that the Granite-Ryolite, we're not really sure of the cause of that, but you can see these other sutures that have happened. In other words, things just came and slammed into this side of the continent. It was like 1, 2, 3, and 4, a series of events that happened. Cross-section of North America showing the subduction zones associated from 1.3. This is when Rodinia came together. This is the supercontinent Rodinia coming together. And D is represented right here by D. Again, you have the continental suture right here. But something weird's happening here. There's a plume that comes up underneath here represented by this area right here. And what this plume does is it tries to bust apart North America. And it's represented by this mid-continental rift right here. So North America almost did this again, and it's kind of funny. They sort of were aligned roughly in the same direction. And North America went over the plume, or Laurentia, sorry. And then this plume just busted and punched its way through. But it didn't come up really so much underneath the continent itself because it was too thick. It did partially, but it sort of came up and diverted around it, and then came up on this essentially the southeast side as we look at it right now. And then you can see the other orogenies right here, and now you have the Grenville. So we go down to E. Where's E? Oh yeah, E's right here. E is showing basically what happened after the rift. So this is actually this is E right here. This plume is represented. It came up under here, but this is after it happened. And then you have F, which is right here, and F is basically showing. I'm sorry. I'm going to go back to E. E is showing that this is showing the Appalachian orogeny starting to occur, and this is the closing of the Atlantic Ocean. I mean the Iapetus Ocean with subduction going under the continent right here, and so that is what you're seeing right through here, which is going to be right in here. And then if F is showing the warping of the Grenvillian area right here, so you have metamorphism occurring here, subduction is occurring, and then mountain building is happening all through here into here, and that's represented through here. And I don't have G, but G is just probably showing the completion and the suture of all of these terrains. G is actually, I'm sorry, G is showing us the Cordillera right here. This is the subduction has now begun to go under the western side of North America, is represented right here. Okay, that makes perfect sense. Oh, I know why this is. So this one's actually E, this one's actually F, and this one's actually G. Huh. So D is actually missing up here. That's a little confusing. I know I had a hard time with that. All right. Well, anyway. Archean Cratons of the Canadian Shield and northwestern United States, including, this is the beginning. We're going to run through these orogenies real quick. So these are Archean age 2.5 billion or older. This would be where we are located in Maine, where I am located in Ogunquit, Maine, the Marginal Way. And these are the Cratons of the Slave, the Ray, the Hearn. These are all up in here. You have the Superior right here, the Nain over here, and then the Wyoming down here. And this is sort of what these pieces looked like prior to uh, North America starting to come together. They were kind of scattered, and they look something like this. Now, these are just in their natural they're in their current geographic positions. In other words, this is where Wyoming is today. These were actually more fit together, so that's why they look the way they do. It's just, think of it as they really should be together. It's just that in order to understand where the pieces come from, it's more understanding to put them in their current positions. So first orogeny happens right here between the Slave and the Ray. You have basically juvenile arcs that formed along here, and then these things slam into each other. It's called the Theon arc, and it's one of the oldest. It's 1.96 to 1.92. Then you have continued closure of some oceans back here, so you have some subduction. I'm not sure which way it's going, but there is subduction occurring, and you can see that actually subduction would be going under here, so this is actually a spreading center. Okay, and this orogeny is now starting to widen, although it says the closure of the oceans. I'm not 100% that is what's going on. I may have misinterpreted that, but it could be. All we know is there's an orogeny right here, about 1.92, 1.86. And then another arc formed right down here, and then another arc. It seems as though in the early, in these around 2 billion or prior, most of your action was just on the sides of the early continental nucleuses, because I don't think there was really enough mass here. So in other words, they weren't really colliding into each other. They were just having, probably the crust was sort of gooey, and maybe it deformed easier, so that makes sense that you would get your early orogenies right along the borders of the cratonic nucleuses. So now we're starting to get these pieces coming together. There's faulting right here. This is called the Yavapai orogeny. Okay, this is pretty well known, 1.86 to 1.84. Basically, these two pieces have now welded onto this piece here. So we looked at it here. Yeah, so whatever's happening, stuff is coming from this direction here, and it's adding land and island arcs off to the left here. And again, there's some small kind of action going on down here, but nothing really huge going on. Now we have the Trans-Hudsonian Belt. This is when these two pieces here have come together and formed a massive amount. This is really the first continent-to-continent suture on this particular on Laurentia. So 1.84 to 1.82 Trans-Hudson Belt Archean fragments are now welded together. They are sutured. There's also some arcs up here that were involved in this, because when it opened, or actually when it's closed, as the oceanic crust is being subducted, island arcs were being created. So there's there's island arcs in here, as well as a continent-to-continent orogeny right here. So this up to this point in time, this is probably the largest orogeny that we know of, at least probably producing the highest mountains in any case. And again, here's Maine right there. So now we are still adding real estate to this. We're starting to get some island arc activity down here. In the next 100 million years, we're going to start getting the Yavapai, and what's going to happen is this whole area down here and along here is going to start, subduction zones are going to form, and we're going to start getting island arcs slammed onto this area right down here. And here we are. So we're starting to see pieces of island arc starting to pop up here, and these are going to start welding onto the side of North America, and they create a series of mountains right here called the Yavapai Province. The Yavapai Province is a assembly of oceanic terrains, much like the Aleutians or the Philippines. Just imagine the Philippines and all the islands in the Western Pacific welding on to the side of Southeast Asia, and that's exactly what this would look like, and that's what that is right there. So anyway, it's very similar to the Indonesian archipelago we see today. A lot of juvenile arcs. When I say juvenile, these are pieces of oceanic crust diving under other oceanic crust. And what it's doing is it is creating island arcs, which we consider juvenile. They're not mature like continental crust. Um, and they're also younger. So anyways, a bunch of these formed along here and then welded onto North America and created the Yavapai mountain range. And then as the arcs accreted and subduction occurred in this area, we started to get volumes of magma being injected into what we call stitching, and all these plutons and stuff from the island arcs, the oceanic crust subducting, basically sent up magma into the crust that adhered onto the side of this continent and basically put granitic and andesitic and gabbroic blobs in here, and now it's literally stitching the rocks to the continent. Now we got the Mazatzal. This is right after the Yavapai. And again, it's a series of island arcs that get welded onto the side of North America. This one's slightly bigger. And it's almost as if this is kind of like the closing of the Iapetus. You know, to me, it seems very familiar because the Iapetus, we have the Taconian, we have the Acadian, and then the continent hits, and it's kind of like this. You know, you have some arcs that formed, and then you have some small pieces of crust or micro terrains, and then more arcs, and then finally the real deal comes along. So, and it's, you know, the time period's not that much different. So I don't know. Maybe that's just a whole series of a ocean closing right there that we do not. I mean, never heard a name for it. So whatever the ocean was there before the Atlantic, I don't know. I mean, before the Iapetus. Anyway, so then something weird happens here. So you got all your orogenies here, you got your early ones here, you got the Trans-Hudsonian here, you got the Yavapai, the Mazatzal, you got the stitching, you got the stitching here. Well, it's as if it wants to do it another time, and for one reason or another, this area does not seem to separate. So in other words, there wasn't another episode, an opening and a closing of an arc or small terrain. But what does happen is massive amounts of lava, felsic lava, actually granites, start invading this area right here. And for one reason or another, the crust, it just does not separate. It does not thin out enough, and this part of the continent never rips off again. In this episode, it almost does, but it doesn't quite. And so basically, we think that, you know, when you do have something rift and separate, it starts out as pretty much felsic because most of the continental crust is felsic, so you got to melt that and punch through that, so you get large volumes of felsic, and then you get the more mafic stuff, and then of course the ocean, the continent breaks, and then you have real mafic oceanic crust start to form. Well, this just never got past stage one. So that's the theory, anyways. A lot of people have always been slightly confused by what exactly this represents. You know, some think it's a back arc area from the during the Granite-Ryolite Orogeny, but the Granite-Ryolite Orogeny was, you know, quite earlier. So you know, jury's still out on that as far as I know. And then we get the Granite-Ryolite Province. Now it doesn't just almost separate, but then it gets stitched, and it produces massive amounts of plutonic rock that you know, is very rich in granites and rhyolite and felsic stuff, and it just does the whole thing. So it doesn't. You get this area, but then you get a whole much larger volume of plutonic injections after that. So it's very, very interesting formation for sure. What's interesting is you see this chunk right here missing, and that will be explained a little bit later. And then we have the Granville orogeny 1.3 to 1.0, and this is of course the arrival, we think, of Amazonia, and this is a very, very large worldwide episode. So this mountain building event is found all over in all continents. You just have to piece them back together, and this is basically, you know, when Rodinia comes together, and that's basically Pangea before Pangea. And again, right here, representing the culmination of continental collisions that assembled Rodinia. And this is when Rodinia, and when you see these mountain building rocks that have been affected by and deformed by the mountain building of Rodinia around, you know, 1.3 to 1.1, you'll see them on all continents, and if you can piece them together, and these are all connected in one big suture of the supercontinent of Rodinia. And then, of course, when we split, again, when mountain range comes together, continents have to split up because it's no longer here. You get massive amounts of granite intrusions that stitched these terrains back together. So it's par for the game. You get the orogeny, and then you get the injections when they separate, and then orogeny intrusions, orogeny intrusions, orogeny intrusions. And the final phase of eastern rifting detached the Argentine Precordial microcontinent from a washout Texas embayment, which is right here. This is actually a piece of Argentina, we think. And the Precordial terrain is currently located in western Argentina. So in other words, we took a piece of us, went away, and we also got left with a piece right here. So it's interesting. So this is a piece, I believe, of the Argentina, but there's another piece over here that got taken away that, I think it's right here, or here, that is North American, and it is now in Argentina. So if these two pieces also fit right near each other, so not a lot of detective work there. And I'm going to end this talk right here, because now we're going to go into the supercontinents through time, and the one we were just discussing was Rodinia. So, but there was a few before it. So tune in next time for supercontinents. Aloha.